Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Alright, so today we are going to continue the properties of Laplace transform. So one of the properties that I haven't shared in the last class is the time periodicity. Okay, so if we have a signal that have a period, repeats and have period, for example, like this one, sinusoidal, okay, it has one period here from the time it started to the point it ends and repeats, so this is time t. Or maybe you have like this signal, okay, it repeats, okay. So to handle or solve this type of signal, we will just consider this one as F1S. Okay, one period is until here, F1S T, and then when it repeats again, okay, so it's going to be F2S. Okay, so what we can do, we just find the Laplace of the first period and then divide it by 1 minus E minus TS. Okay, so T is the one period of time. Okay, for example, we have this signal. Okay, this is minus 1 to 1 and this is 1. Okay, so this is in time domain. Okay, so the question is, how are we going to find the Laplace transform of this signal? Okay, so from the equations we know that the time exists from minus 1 to 1. Xt, this is the formula, xt e minus st, okay, dt. Okay, so what is xt here? Xt will have the value of 1 e minus st dt. Okay, so we integrate this one from minus 1 to 1 is equivalent to 1 over minus s e minus st from minus 1 to 1. Okay, so if we substitute here, e minus plus e minus minus s over s minus e minus s divided by s. Okay, so also defined by 1 over s, e s minus e minus s. Okay, all right, so this is the Laplace of this signal. Okay, but what if the signal repeats periodically from minus 1 to 1 and then 2 to 4? Okay, so the period of this one is here, t equivalent to 3. Okay, now we are using the formula. So xs, the whole signal xs will be x1s divided by 1 minus e minus t s. Okay, we refer to this formula, this one. Okay, okay, so we have defined x1s previously here. Okay, so this is x1s. Okay, but how about the rest of the signal? We just use this one, 1 over s e s minus e minus s divided by 1 minus e. The function is 3 s. Okay, the function of time is 3 s. Okay, so this is the solution of this periodic signal, time t. So this is in s. All right, so for this example, again it repeats, okay, until here. All right, so what is this functions? Okay, you find you're using y equivalent to mx plus c. Okay, so this is t. Okay, so the functions just now, let me just redraw here. This is t, but it exists from ut minus ut minus 1. So this is ut minus 1. So this is ut minus 1. And the first one is ut. Okay, when you minus the second one with the first one, so it will only exist here. Okay, so that's why this is t with the amplitude of 2 here. Okay, and it only exists from ut minus ut minus 1. Okay, this will make it only exist here. Okay, right, so since it has more functions periodically, okay, so we will find the first one only, f1t, and make it fs. Okay, so when you expand the functions to t ut minus 2t ut minus 1, okay, so if we see this one, the function is not shifted the same with the function u and function t. Okay, so we have to expand it to become ut minus 1 plus 1 minus ut minus 1. Okay, so we want to take this one is the same with the function ut. Okay, so now we have 2t ut, the original one, minus, now we have expand this 2t minus 1 multiplied by ut minus 1. Okay, so if you can see here, it's minus 1 and minus 1, so that's mean it shifted the same as the function, step function ut. Okay, and this one will let just 1. Okay, no need to have a function t. Okay, because it, this one multiplied by this one, okay, and this one multiplied by this one. All right, so now we have found the part by part and ensure that it shifted the same one by expand the function t. Okay, so now we exchange. Okay, for the first one, this is Laplace. For the first one, 2t ut. Okay, so 2t in the table, okay, we use 1 over s squared. So the 2 is the coefficient. Okay, so 2 divided by s squared because 2t. And then this one is 2t also, but shifted by minus 1. Okay, if shifted according to the properties, okay, time shift, we will multiply it by e minus s. Okay, so this is the function t time, t equal to 1, divided by s squared. So this is the original signal, t. In the table, t is 1 over s squared, but it has shifted, so we multiply by e minus s. Okay, and then the last one is a step function. Okay, if step function in in Laplace or frequency domain is 2 over s, is 1 over s actually, but since there is a coefficient 2, it will become 2 over s, and then it's shifted by minus 1. Okay, so it has to be shifted by e minus s. Okay, so now we have complete the function f1. So the function f1 will become 2 over s squared. You just make the denominator the same. 1 here, 1 minus e minus s e s. Okay, so this is only 1 s, so we have to multiply it by 2. Okay, here to make it s squared. Okay, now we settle the f1s, only this one. But since it has a period, okay, so we are going to use the formula given in the table. So f1s divided by 1 minus ts. Okay, so we identify the time and also the f1s and substitute in the equations. We will get this one. All right. Okay, so another example, if you want to find the initial and final values of the function. Okay, so the Laplace transform is Hs. Hs is a transfer function, mean ys divided by xs, sorry. So equivalent to 20 divided by s plus 3, s squared plus 8s plus 25. Okay, how we are going to find the initial and final value? Okay, to find the final value, initial value means the early value which sh at t equal to 0. So we will using this formula. This is the formula for the initial values. So s multiplied by the hs. So this is the hs. Okay, the s is based on the formula, and make s approaches 0 or substitute it to infinity. Okay, s approach infinity. So when you substitute here, the final value is 0. Okay, sorry, the initial value is 0, and then we go to the final value. This is the formula. Okay, final value mean h at time t into infinity. Okay, when we multiply by s according to the formula and substitute s equal to 0, so again we have this final value is 0. Okay, so we identify the roots is 3, so s equal to valent to minus 3. So this is the poles at here. Okay, so this is the region of convergence in the left. Okay, all right. Okay, so the next properties is the time differentiation property. Okay, if we have time differentiation property, that means we want to differentiate a function xt. What we have to do is we identify the order. Okay, how many derivation? So the s will be follow the derivation level, xs the function's Laplace. Okay, and then we have also the full formula to solve the differentiation property, like this one. Okay, so we follow this one. If there is initial condition, the first derivation and also the second. Okay, okay, we have, I'll just continue here. Okay, so basically we will use this concept, the differential equation, as algebraic equations. Okay, so most of the time we will deal with differential equation. Okay, so time domain analysis will solve the differential equation by finding the output in terms of Laplace and also the input in terms of Laplace, which is xs and ys. Okay, if we have the input xt as a linear combination of exponential est, so we know that hs, the system response of the impulse response, will be looks like this. Okay, so hs is actually ys divided by xs, the output, divided by input. Okay, what is transfer functions? Transfer function, or known as the system's response. Okay, like what is the output will change after you put it some input. Okay, all right, so we recall that a differential equation can describe a system. Okay, So impulse function HS is also a complete characterization of system, means we define the output divided by the input. Okay, so if we have the original differential equations is this one, we can have the ys part and also the xs part, okay, from here. So from this we can derive the impulse function by dividing the ys and xs. So you have to expand the value of ys and xs. Alright, let's see this example. Okay, so the application to integral differential equation mean we have the differential and also the integrations. Okay, so let's say we have d squared vt over dt squared plus 6 dv over dt plus 8 vt equivalent to 2 ut. Okay, so this is the input part and then this is the output part. It also gives you the initial value. So how are we going to use this? Okay, so first of all, we see that this part, which I have informed just now, what is the suitable differentiation will be. So it is a second degree, so will be s squared vs minus s still there multiplied by the initial condition, okay, according to the differentiation property, okay, minus v prime 0, which is the initial conditions. This is the first order, this is the single value, no order, okay, plus this second one, if only 1 degree, so now it becomes 6 multiplied by s vs minus v0, okay, this is the last point, plus 8 vs, okay, vs is the vt equivalent Laplace, okay. At the input part, it will become 2 divided by s. Why? Because the Laplace transform of a ut step function is 1 over s, okay, multiplied by 2. Okay, so that's mean if we want to substitute this value, it will become s squared vs minus s, the initial value is 1, minus v prime 0 is minus 2 to 2, okay, plus 6 v 6s vs, okay, minus 6, minus 6, the initial condition is 1, 6s vs minus 6 plus 8 vs equivalent to 2 divided by s. Okay, so now we have substitute the initial conditions and left only vs. Okay, alright, so now it become s squared vs minus s, okay, same here, s squared vs minus s plus 2 here, 6s vs, 6s vs minus 6 here, minus 6 plus 8 vs equivalent to 2 over s, okay. So now we factorize vs and put the one without vs at the right side here, okay, and we simplify it, become s squared plus 4s plus 2 divided by s, okay. Now vs will become s squared plus 4s plus 2 divided by s, okay, s plus 2 multiplied by s plus 4, okay. You just rearrange here, okay, this one go down. Alright, now we have the numerator is here, s squared divided by s power of 3, so m less than n, So we can do partial fraction equation. A divided by S plus the second one, B divided by S plus 2, and C S plus 4. Okay. Substitute S equal to 0 and find the A, B, and C. Now we have 1 over 4 divided by S, 1 over 2 divided by S plus 2, and 1 over 4 divided by S plus 4. So A, B, and C. Okay. So 1 over 4 divided by S, we know it's a delta or 1 here, the inverse Laplace transform. Okay. So 1 over 2, or here we rearrange, okay, the coefficient will become 1 over S shifted by E minus 2t, or we know that this is the alpha, okay, from the table, and also 1 over 4 E minus 4t. Okay, either you are using the shifted properties or directly from the table. Okay, ut is it's a causal, so now you can find the value of vt. All right, another one is dy over dt plus 5yt plus 6 integration of y tau d tau equivalent to ut. So it also gives you the initial condition y0 equal to 0. Okay, so for this one, okay, dy over dt, so it will become sys minus y0. So this is for the dy over dt part. Plus 5yt, which is ys, plus for integration, if we have integration, we make it as 1 over s multiplied by 6, the coefficient, and the signal itself. Okay, equivalent to 1 over s is for the step function. Okay, so when we substitute this, the initial condition, this one become 2. Now the equation, since there is a s here, we want to make the s at the numerator, so we multiply by 2, s squared ys minus 2 here become 2s plus 5s ys plus 6. Okay, multiply, so it will lose this one, become equivalent to 1. Okay, now we rearrange, ys become s squared plus 5s plus 6 equivalent to 1 plus 2s. So you put all the ys factorize here, and without the ys at this part, the right part. So now we make ys equivalent to 2s plus 1, rearrange this, divided by s plus 2 multiplied by s plus 3. Okay, so this one, the numerator degree is also less. Okay, so we find a and b and substitute in the equations. So for this one, you're using the Laplace, minus 3 is the coefficient, e minus 2t plus 5e minus 3t. Okay. All right. So we can also have the transfer function, which is ys divided by xs. Okay. It can be voltage gain, where V out divided by V in, or a current gain, I out divided by input I, or impedance V divided by I, or admittance, the inverse 1 over V. Okay, so this is the condition. If the input is delta t, so xs will become only 1, so the output will become the hs, input ht, impulse function. Okay, let's see this example. The output of a linear system is yt. Okay, so output is 10 e minus t cos 4t ut. The input is e minus t ut. Okay, so the transfer function, which is hs, will be equivalent to ys divided by xs. Okay, so now let's solve xt and yt. Xt from the table 1 over s plus 1, and the 10 is the coefficient, e minus t is the shifted value. So the function cos 40 ut in the table is equivalent to s divided by s squared plus 2 squared. Okay, and then we shifted it, so s now become s plus 1, and this one also become s plus 1, part of the shifted time shift property. Okay, so we can find the hs by dividing ys and xs and simplify the equations. Alright, so now we want to find the xt. To find the xt, okay, we have to simplify this equation. So in this case, the degree of the numerator and denominator, or m and l, is equal. Okay, so what we can do is we have to find the equivalent functions not using the PFE. Okay, so we have to divide 10 s, okay, here, then s squared, then s squared plus 20, s plus 20, s plus 20 divided by the denominator, which is s squared plus 2s plus 17. Okay, so multiply by 10, then s squared plus 10 minus 2, 20s plus 170, which is equivalent to 160. This is 10, 160. Okay, so now it will become hs 10 plus 160 s squared plus 2s plus 17. Okay, so or we can or it can also be rewrite as this one, and then we find the equivalent Laplace is 10, will become 10 delta t. Okay, minus 40 et is from the time shift, and then this one from the equation of sine omega divided by plus s plus omega squared. Okay, so omega here is 2. Okay, now you can find the ht. Alright, so in order to define a system, we want a stable, usually we want a stable system. Okay, and causal. Okay, so a ball sitting in a valley with rough sides, I mean there is a resistance there, an impulse input will set ball in motion, but the ball returns to resting state. So that means it's a stable system. But if there is no friction or frictionless surface, the ball is stable, but it will move around, and an impulse cause the ball to be set in motion forever, means it's partially stable. Okay, but so this is partially stable, this is stable, and this is unstable. So we we will keep the ball falling forever. Okay. Okay, so this is a three category of stability. So this is the example, but actually stable in a bounded input and bounded outputs is defined as three things, okay, or three elements. The first one, the impulse response, is absolutely summable or integrable. That means it have finite values. Okay. Number two, the region of convergence of a system is called bistable if it exists at the left part of the system, the alpha, okay, or the poles. And the third one is the characteristic equations. If all poles are in the left half plane, like this one, okay, poles are all here, so it's a stable system. So this implies that the roots of the characteristic equations are all negative, or at least have one negative real part. Okay, so if we can identify A in the first order, so it will be more than 0, and for the second order A and B are more than 0, or third order A, B, C more than 0, and if we multiply A, B are more than C, so it also stable. So these are the three conditions for stability. Okay, so I will stop until here for the next class. Thank you very much for your attention. If you have question, you can directly message me or private message. Alright, thank you very much, and sadaqallahul azim wa billahi taufiq wal hidayah. Wassalamu alaikum warahmatullahi wabarakatuh. Thank you.